Military land vehicles operate in continuous physical extreme. Their environments are characterized by heavy multi-axis vibration, severe thermal shock, and unstable 24-volt electrical networks. Inside these platforms, complex arrays of delicate logic processors, radio frequency transmitters, and power controllers must execute flawlessly to maintain operational integrity. Treating the enclosure as a passive box, a hollow metallic shell containing empty air and a circuit board, results in catastrophic failure. The dead internal volume creates a resonant chamber for vibration, traps heat, and allows electromagnetic interference to bounce freely. To survive, engineers utilize skin-tight packaging. Here, the enclosure is a highly integrated boundary layer. The chassis walls simultaneously act as the structural backbone, the primary electromagnetic shield, and the solid-state thermal heat spreader. For a land system controller, this boundary is governed by three rigorous benchmarks. MIL Standard 810 dictates the environmental survivability. MIL Standard 461 enforces electromagnetic compatibility. And MIL Standard 1275 defines power quality thresholds. Achieving compliance means resolving deeply conflicting physics constraints into a single, high-density, miniaturized volume. A requirement for thicker shielding directly opposes the need for weight reduction, while tighter sealing restricts thermal dissipation. Survivability is not a feature added at the end of the development cycle, it is the architecture itself. We will examine these constraints by constructing a theoretical reference model, Enclosure X1. The first constraint in miniaturization is mass. Engineers must strip away excess weight without sacrificing the material density required to absorb heat or the mechanical stiffness needed to survive shock profiles. Standard stainless steel is too dense for lightweight applications. The primary competition for high-performance stins exists between 6061 T6 aluminum and magnesium AZ91D alloys. Aluminum is traditionally injected into molds through high-pressure die casting. This process relies on turbulent fluid flow, which can trap air and create porosity in the metal. To compensate, designers must maintain a minimum wall thickness of at least 2.0 millimeters. Magnesium fixamolding offers a physical alternative. By heating magnesium into a semi-solid slurry rather than a total liquid, the material can be injected with laminar flow, entirely eliminating the turbulent air pockets. Fixamolding casts magnesium walls down to 0.8 millimeters, massively reducing size and weight. But this reduction incurs a thermal penalty. Aluminum's thermal conductivity is 167 watts per meter Kelvin, making it a vastly superior heat sink compared to magnesium's 72. To manage heat in a miniaturized space without fans, engineers rely on 3D component nesting. This technique eliminates internal air gaps entirely, ensuring high-power components make direct physical contact with the machined enclosure walls to transfer heat through conduction. Leaving a microscopic air gap between the processor and the chassis isolates the component, leading rapidly to localized thermal runaway and the destruction of the logic board. To pack these components so tightly against the metal, designers replace flat circuit boards with rigid flex printed circuit boards. The flexible substrates allow the electronics to bend and conform perfectly to the complex internal geometry of the metal shell. Removing dead volume in this manner forces the assembly process to operate on sub-millimeter tolerances. Any deviation in the metal casting or the board placement will cause mechanical interference, crushing delicate surface mount components during assembly. Substrate selection establishes the device's thermal capacitance and the precise spatial geometry of the entire system. The enclosure must secure its electromagnetic boundary. MIL STD 461G tests if a device can operate in heavy spectral noise without absorbing or emitting interference, a discipline governed by the laws of electrodynamics, codified by James Clerk Maxwell. A pervasive engineering error is assuming that the total area of a hole dictates how much radiation escapes the enclosure. Area is largely irrelevant. High-frequency electromagnetic leakage is determined entirely by the longest linear dimension of a gap. The core rule for a Faraday cage: the maximum dimension of any opening must be less than lambda divided by 20. A continuous 100mm gap functions as a slot antenna, where internal noise resonates and broadcasts outward. To seal this boundary, engineers compress a conductive EMI gasket between the metallic enclosure halves, creating continuous electrical contact across the entire seam. The conductive elements inside the gasket act as hard physical shorts. They electrically divide that long 100mm slot into dozens of harmless sub-wavelength segments that block RF propagation. None of this shielding works without a stable electrical reference. The entire chassis must be tied to the vehicle's ground through a dedicated earthing and bonding subsystem. A grounding stud requires a precise hardware stackup: the bare chassis ground, a conductive finish, an anti-rotation tooth washer, the ring terminal strap, and a securing nut. The contact resistance across these faying surfaces must remain below 1 milliohm. If vibration causes the nut to back off and resistance spikes, lightning or pulse currents will arc across the joint, destroying the equipment. Structural verification standards, like IEEE 299, will certify that the empty box successfully attenuates external fields, but MIL STD 461 evaluates the entire active system. A perfectly sealed, heavily shielded box will fail the 461 standard instantly if a single exiting cable lacks proper 360-degree shielding. The cable will simply pick up the internal noise, bypass the metal walls, and transmit it into the environment. Isolating internal logic from external spectral chaos requires strict management of discontinuities, tracking electrical impedance in milliohms and physical apertures down to the millimeter. The mechanical and electromagnetic boundaries must ultimately interface with a biological operator. Ergonomics in industrial design represents a rigid biomechanical constraint critical to preventing system failure. Legacy enclosure design often relied on the statistical fallacy of the average operator. Because human proportions are not perfectly correlated, designing solely for the 50th percentile median actively excludes half the potential workforce from operating the equipment efficiently. Modern defense and industrial standards, including ISO 11064 and MIL Standard 1472, mandate that spatial geometry accommodate the user population from the 5th percentile female to the 95th percentile male. This wireframe demonstrates vertical functional zoning, dividing the enclosure into bands based on biomechanical efficiency. Zone 1, the visual and cognitive band, is between 1,000 and 1,700 millimeters off the ground. Critical human-machine interfaces are placed here to align with the natural line of sight. Placing primary displays above the 1,700 millimeter mark forces a 5th percentile user into continuous neck extension, inducing a rapid cervical fatigue and severely degrading their cognitive reaction time. The physical interaction constraints extend beyond height to include manual actuation limits for safety controls. The mechanical force required to activate an emergency stop or critical disconnect must not exceed 5 pounds, or 22.2 newtons. This metric immediately rules out the use of stiff, heavy rotary disconnects in accessible areas, forcing engineers to specify lever-assisted handles or push-button actuated contactors to ensure reliable operation under duress. Forcing an operator to adopt an awkward posture or exert excessive force increases the probability of operator error. Ergonomic noncompliance is a latent failure mode. Engineering a military controller requires the simultaneous execution of thermal dissipation, electromagnetic isolation, and anthropometric geometry. Enclosure X1 is the physical manifestation of synthesizing these deeply competing constraints. Altering a single variable ripples through the entire physics model. Thinning an aluminum wall to save weight instantly degrades the thermal mass available to the processors and reduces the structural stiffness required to properly compress the EMI gasket. These systems are destined for the heavy distribution networks of tactical land platforms, where vibration, voltage spikes, and environmental ingress are guaranteed threats. Compliance with MIL Standard 810 and MIL Standard 461 cannot be achieved through a checklist applied after the fact. Survivability must be engineered into the foundational geometry of the hardware itself.